Welcome to Lecture 5 of CS224D. Today will be one of the most exciting lectures in the sense that, one, we'll start talking about the project, and two, we'll actually define a multi-layer neural network and go through the algorithm on how to train it. In some ways, this will end sort of the first introductory third of the class. So for those of you for whom things were going a little too fast, you definitely want to make sure you go through all the equations today very carefully, come to our office hours, make sure you really understand this, because in the end, for the next third, we'll really just take those basic ingredients that we finish today and just put them together in various interesting ways. And for those of you who so far the lecture has been too slow, good news. So this today will be the last slow lecture where we'll go through all the painful detailed equations, and we can go more high level after that. And hopefully the vast majority of you will just learn a lot today and be able to continue going through the class. Before we jump into today's lecture, are there any questions so far organizationally? The problem set is going to be due this week, so we added 2 days, so it won't be due tomorrow, but on Thursday night at midnight, right? We'll have extra office hours today also, today and all the other days. So if you have any questions, do come to office hours. All right, so let's jump into the class project. It is basically the most important part of the class and also of your grade. It's 40% of your grade. And in some ways, it's also the most lasting result of the class. We often see that people who have a really amazing class project, they use that to apply for jobs. You might put it on your CV. So it really is with you for a long time if you do a really good job. And in order to facilitate you being able to really create an awesome final project, we also make the last problem set a little easier. Instead of making you implement 2 complex models, you can choose one or the other. So definitely start early, clearly define your task and data set, and we'll go through a couple of steps now for the 2 types of class projects that most of you will probably fall into. There's a third type, which is sort of the theoretical analysis, but if you want to go down that route, definitely do talk to me first. It's very hard to do interesting theory on neural networks. It's possible, but it's very non-trivial. You probably want to be a physics or math PhD student to go down that route. So do talk to me before you go down a theoretical one. Most of you will either apply an existing neural network type model, most likely one that will go through class, we'll go through all the major ones, and apply it to some interesting new task. And then the second one is also harder than the first one because in some sense it's a superset. You have to do all the stuff of step 1 or of the first project type and then implement your own interesting new model. So let's go through the steps that you'll have to most likely do for a successful class project, and then we can move on to backpropagation and neural nets today. So a handful of different groups have approached me and asked about summarization, so I'll use that as an example for a potential class project. I'm not saying this is the best class project you could possibly choose or the best task, but it is just one potential choice. So step 1, define your task. What kind of ideally natural language processing task do you want to solve? Like I said before, it doesn't have to be natural language, it could be programming languages or other types of genetic languages, so we can define this pretty broadly, but the default should be define some NLP tasks you want to solve. And then the second step is you want to find your data set. And it's very important when you submit your proposal and when you by your milestone to really have your data set nailed down. So in the beginning we often see project proposals that are very ambitious, and then at the milestone you still don't even have properly defined your data set. So once you define your data set, in most cases the way you do that is finding an already existing academic data set that has the huge advantage that you already have baselines. If you beat the baselines or research models that were run on that data set, for sure you have some amazing result, and you could even potentially publish a paper about it. So in the case of summarization, a quick Google search will show you that there's a document understanding conference, DUC, and that actually has several summarization data sets, where you have a large body of text and you have human-generated summaries. The other alternative for your data set is that you can define your own. In some sense, that's harder because now you get some result with your own implementations and you don't know where you stand. Is that an amazing result, or is that a pretty standard result that people had 15 years ago? You wouldn't know. If you're a graduate student or a master's student and you do some research, the coolest kinds of projects often come from connecting this class to your own research. So maybe you're in education and you could have some data set where you have student essays and you want to grade them, for instance. In the case of summarization, maybe you could build your own data set based on Wikipedia. You could use the intro paragraph and then the rest of the article, and you try to summarize the rest of the article to become your introduction paragraph, for instance. Again, this is harder. You probably won't get that many bonus points for creating an interesting data set that's not really deep learning for natural language processing. It'll just be crawling. You could go to Twitter, blogs. In some sense, you want to be creative, and creativity will give you a little bit of a bonus. But if you spend the entire quarter just crawling a data set from somewhere on the internet, that is not really deep learning, so you won't get a really good grade if you get stuck on that. So do start early, especially if you want to collect some data set that isn't just readily available like Wikipedia. If you want to use news articles or blogs or Twitter, there's only so much you can crawl in a certain amount of time before most websites block you and so on. And so you want to start early if you want to collect your own data set. All right, the third step is you want to define your metric. So basically, in most tasks, you want to basically use the well-established metrics for that task. Don't make mistakes such as like using, for instance, there's a task called semantic role labeling, where you basically look at who is an agent, what are instruments in a sentence, and most things aren't agents or anything. They're just verbs or adjectives, determiners, and so on. And so one big mistake would be to use accuracy to evaluate such a problem. Similar with named entity recognition, where most things aren't specific named entities and they're just general words, and so the category of null or not a named entity will be potentially 80% of your entire data set. Now if you use accuracy instead of F1, who here knows the difference between accuracy and F1? Could you raise your hand? Okay, not as many as I'd like. So I guess we'll go over that then in the next lecture. So well, we actually talk about tips and tricks on how to evaluate stuff. But basically, if you use accuracy and 80% of your data set doesn't have a named entity label, you could just get 80% accuracy by just saying nothing is a named entity. Right? And that would not be an interesting result and not a good evaluation metric. So know which evaluation metrics are standard for your task. And again, if you can find things online and well-established research papers, just come to my office hours and we can chat about that. In the case of summarization, you will very quickly find, if you Google something like evaluation metrics for summarization in natural language processing, things like that, the so-called Rouge metric, which is recall-oriented understudy for gisting evaluation. It's basically a simple n-gram overlap type metric that takes the human summaries, takes your summaries, and looks at how many n-grams are overlapping between the human summaries and the one your algorithm generates. All right, so now you know your task, you know your data set, you know your metric. Step 4, and that's very important, split your data set. If there's one thing that every single good machine learning project in these kinds of supervised domains should probably do, it's having a proper train split, development split, and test split of your data set. In many cases of the academic data sets, it often comes pre-split. You're basically going to train your algorithm on your training split, and then you can evaluate and develop on your development split or your dev split. And only in the last week or so before you hand in your final project are you going to run it on the final test set. And that way, hopefully, you didn't contaminate your test set, and you really have now a number that is indicative for how well your algorithm would do in the real world on data it's never seen before. So if you only show me the results on your training split, then you just know how to overfit a model that potentially you wouldn't generalize. If you now tune your hyperparameters so long that you do well on your def split, but now you don't do well on your final test split anymore, then you kind of did your own internal gradient descent on the hyperparameters, essentially, and you're also kind of overfit, and you didn't develop an algorithm that's very general. So it's very important to split your data set, and it's also very important to not look at your test split if you do error analysis and you're trying to develop, and improve your algorithm. Are there any questions about the first 4 steps? All right, so step 5, establish a baseline. Basically, you want to implement the simplest model first. In many cases of supervised kind of natural language processing algorithms, that could be just logistic regressions on unigrams and bigrams. So just, very simple logistic regression on your word identities. So of the one-hot kinds of vector representations that we used. And then you compute your metrics on your train and your development split. You analyze your errors on your development split. And if your metrics are amazing and you actually don't have any errors, well, you're unfortunately done a little too early with the class project, or with the first attempt at a class project, because then your problem was just so easy, you kind of need to restart and come up with a harder either problem or a harder data set to solve your problem with. Assuming you had some errors and the simple baseline doesn't already solve your problem, then you can go on and implement an existing neural network model and again compute the metrics on your train and def split, analyze the outputs and errors, and that is kind of the minimum bar that you should achieve for this class. But notice how it's step 6, you don't want to get stuck at step 5 and then you only have 3 more days and you don't have enough time for the actual juicy bits of this class, which is that deep NLP model. And the last 2 tricks or important steps for your class project is to always be close to your data. I was a head TA for 229.2, and is a very large class, and there are lots of different groups, and sometimes I would notice how some groups run a bunch of experiments and get error metrics and have nice graphs, and then I asked them, like, why does it fail? Where does it fail? And they have no idea. They never actually looked at the text of the actual problem. And so if you do that, you really can't gain intuitions of why your model is failing. Why did this hyperparameter create this bump in your F1 score, for instance? So you have to be close to your data. So the best kinds of projects and the best groups, and this is really a life lesson in some ways, the best data scientists and the best people dealing with any kind of machine learning in the real world are close to their data. They visualize their data sets, they collect summary statistics. For instance, if you look at your summary statistics and you notice how one class is like 95% of your entire data set, and then another one is 2 or 3, and another one is just 2%. So let's say you have 3 classes and one class is 95%. Just looking at that metric in the beginning will make it very unlikely that 1, you should use accuracy as your evaluation metric. 2, it'll be very hard for a machine learning model in the vanilla style to be able to solve that kind of problem easily. You'll have to do some tricks for so-called skewed data set classes and so on. And these are things that if you come to the office hours and you have some visualization to show and you say, oh, look, this is what an example input-output looks like. This is my class distribution and so on. And this is maybe an error for our baselines, then the TAs and I can help you a lot more also and understand and solve your problem. So be close to your data and analyze how different hyperparameters affect your performance by looking at the actual errors that the actual system makes. And the 8th one is, try out different model variants. And the nice thing is, after today's lecture, you have all the important Lego pieces, the basic ingredients. And in the next third, we can really go through a variety of different kinds of models. We'll have, word vector averaging models. You can have the fixed window neural network models that we'll discuss today. And then you can go to much more interesting ones that can incorporate larger amounts of context in your text. Corpora, like recurrent neural network models, recursive models, and convolutional neural networks. So you'll have a nice tool set, and by the end of the class, hopefully you can use those. The last third of the class will be more about understanding when to use which ones and really understanding what's going on in the research these days and understanding more of the subtleties. And the next third, so the next 5 lectures, we really introduce these various different models to use. So ideally, you can try different ones. All right, so this is these are probably the 8 steps that most of you, and you don't need to obviously do all of these. It's enough if you have a good intuition of why one would work better than another and just choose one of these models. Unless it's the word vector averaging model, that's a little too basic. That's just using problem set 1, or these two are just using problem set 1 and doing something. But the other ones you'll actually implement in later problem sets, and then you can do interesting stuff with them. All right, are there any questions about the first type of class project? All right, so why is it harder to build a new model and do that as your class project? Largely because you have to do all the steps I just described and then gain some intuition of why all these existing models are flawed and how they cannot possibly solve the task that you want to solve. And then you want to talk to other researchers, come to my office hours a lot, and implement new models. And that is essentially a research problem. So if you have lots of classes and you're not that excited about implementing new research, this is probably not the right task for you. It's better to have an interesting application of existing models. But if you're really into this, this is really, I think, one of the most fun you could have in this class. You're going to want to set up an efficient experimental framework so you can very quickly iterate over your ideas. You have like, oh, maybe I should condition this decision based on some other vector, and you'll understand more what that means in the next coming lectures. But you want to very quickly be able to iterate. So for the example of summarization, here's a way that I would go about doing this such that you'll have intermediate goals that wouldn't make you fail the project, and you already have something to show. So like I said in the beginning, you want to build the simplest model first. So you just take some standard off-the-shelf machine learning, like logistic regression on unigrams and bigrams. Then your first neural network model can also be a very simple model. You can just take the average of word vectors, for instance, for each paragraph, and then find greedily other paragraphs that are very different in terms of Euclidean distance to those word vector averages. So that is a model that I could probably implement in 45 minutes, and you should be able to implement in about at most a day already now if you have your data set. And then you can do something more sophisticated, like you could implement a language model, which we'll describe soon, or an autoencoder, which is another type of neural network we'll go over soon, and implement something slightly more complex, but not insanely complex. And then if you really want to push the boundaries of what's possible today, you can have a stretch goal. And for summarization, for instance, that could be using a recurrent neural network, which we'll cover in the next lecture, and actually try to generate your summary instead of just finding extractive summaries, or finding paragraphs that fit well together and you just put them together in a new way. But they're existing paragraphs. You could try to ingest all the content of an article and then try to actually use a neural network model to generate the summary. This is pretty sophisticated stuff. It's a research idea. Nobody's ever gotten that to work. I don't know if anybody's ever tried. So this is kind of a stretch goal. So if you really want to push the state of the art, maybe even publish a paper at the end of the class, that would be sort of an epic outcome. That would be kind of A++ kind of outcome. It's unlikely anybody's able to do it, but it would be really exciting. And you can, those kinds of things, you can also then try and have it with smaller kinds of documents. So maybe your document just has like 10 sentences and you want to get 1 sentence out and see if it works with that. So basically try to have simpler models first, have some results, and then go for some more interesting results. People asked about project ideas. So here are a couple, and those are by no means exclusive or exhaustive. I mean, you can really your imagination is the only thing that should hold you back here. So some simple things, summarization. Named entity recognition is something that we covered a lot. So you could just try to extend that to more different classes. Try a couple of different models, different hyperparameters, different data sets, and see what you can do. I gave here one paper that is very common, or sort of an example paper. Again, there are lots of other papers out there. For this, this one here is a particularly interesting one. It's called natural language processing almost from scratch. So here the authors actually show that the same kind of window-based neural network that we covered in class, and then we'll go through all its details today, can actually solve part-of-speech tagging, named entity recognition, chunking, and a couple of other tasks. So it's an interesting paper to read. You can try to do simple question answering. This is a paper with Moed Ear and Jordan Boyd-Graber and me and some others, where we basically use a neural network for factoid question answering. So it's a quiz bowl, it's a challenge. It's sort of like Jeopardy, but yeah, for trivia facts, and you can use a neural network to try to answer trivia facts in a sort of competition style. That would be a pretty interesting project. There's a lot of stuff that you can do in that space. You can go all the way if you have some image background. You took 231N. You can try to generate or map from images to sentences. That's a pretty exciting current research area. And there are a couple of different papers. Here's one by me that just finds the right sentence that describes an image, and another one by Andrei Karpathy and Fei-Fei Li, who gave 231N last quarter, is basically generating image descriptions from an image vector. So in images will also just be vectors, and we'll actually cover the models that they used in the next couple of lectures to generate a sentence description. This is some pretty nifty stuff. You could do entity level sentiment. So instead of just saying this entire document or this entire sentence is positive or negative, you can have sentences like the iPhone screen was great, but maybe the battery life wasn't. And so now you could say, screen is positive and battery life is negative. So look at more sort of word-specific or entity-specific sentiment. You can also say, the iPhone was great, but the Android was better, or the iPhone was okay, but the Android was better. And then you could say, Android in this context is positive, but iPhone is maybe more neutral. And so this is basically the idea of entity-level sentiment, and there are tons of interesting things. You can apply different models, basically starting again with the simple window-based model. One fun thing that you could also do is to actually go on Kaggle. So this is a machine learning competition website that actually still has a couple of old competitions up. So one example, for instance, is a algorithmic scoring algorithm, a scoring algorithm for student-written short answer responses. So imagine you ask students a question, they have to answer. You have now 500 correct answers, and some that have lower scores from other students, and you want to have built an algorithm that can automatically grade the next incoming question. It'll be something that all the TAs for the rest of life and eternity will be very grateful for if you could solve that very, very accurately. And I think there are other sort of NLP-related challenges on Kaggle.com. And the nice thing here is also that you'll actually see how well your algorithm ranks compared to a lot of other people's approaches. And you can try to really use deep learning only to solve that, which would be very impressive if you could actually get even in the top 5 using only deep learning models. It's been done before, but it's not easy. And then if you really don't feel, oops, all right. PowerPoint crashed, showing everybody my email. Let's not do that. Wrong one. So if you don't feel very adventurous at all, as somebody asked for sort of a default class project, And so one that would make sense for this is sentiment classification. There's a nice data set that we collected here at Stanford. And there are lots of nice deep learning baselines already. So if you get whatever performance you get, it'll be very clear how well your algorithm does on this data set. The data set's already split. The metrics are clear. So this is sort of a nice default class project if you just want to implement something and see how well you can tune a deep learning model. And we'll actually cover a lot of the models that get the best performance on this data set in the next couple of lectures also. All right, so this is all I'm going to say today about the projects. Are there any questions about projects? All right, so let's get started with our more powerful window classifier. So we'll basically revisit this idea of a window-based classifier, and instead of classifying various different things, we'll basically do a very simple task of basically trying to classify whether the center word in each window is a location or not. So it's again sort of a simpler subset of named entity recognition. Just, is it a location or not, the center word. So in the last lecture at the end, we basically defined our neural network with a single hidden layer with the following two steps here. We had our linear layer, which we'll define as Z, which is just a matrix multiplication WX plus B. And then we had an element-wise nonlinearity here, like the sigmoid. Basically, once you have these neural activations, this neural activation vector A here, you can kind of see that as your feature set again, and you can compute any kind of function on top of that. One thing that we had covered before was the softmax, and another one, which is even simpler, is sort of an unnormalized score. So here the score would say is higher if the center word, or should be higher, and we'll train this model for it to be higher, if the center word inside our window X is indeed a named entity. And this is just a simple inner product. We sum up, have a weighted sum of all our activations here of our first hidden layer. Are there any questions about that definition? Okay, so basically this is our 3-layer or one hidden layer neural network, and we'll basically define this again over a window. So here, if our window, each word vector, let's say, this is a toy example, of course, word vectors will be higher dimensional, as you know from your preset 1. But in our toy sense example here, each word vector has 4 dimensions. We have 5 vectors. So our matrix W will be an 8, and we have 8 hidden units. So we'll have an 8 by 20 matrix. And this will define our first neural network hidden layer. And then U will just be a single vector. And again, we can define the entire neural network either through its steps here or in one single equation. And those kinds of equations will get more complex as we have more and more hidden layers. All right, so the main intuition of why we couldn't just have on top of the word vectors here directly our softmax. Right? This was the model we derived in all its gory details before. And it will probably give you some reasonable performance, just capturing specific locations right away or specific words in one location. But really what you might want to have is actually interactions between words in different positions. So maybe you only care about in the second position if in the first position you've seen some word vector like museums. Right? So the hidden layer will actually allow you to have these input vectors interact in certain ways and only activate the high-level feature for the overall scoring if you have a combination of things in your inputs. Okay, so let's summarize the feed-forward computation of the scoring function and define a sort of accompanying objective function. So we have here a score for every window with the center word being a location, and we want that score to be high. And then we have a corrupted window or an incorrect one, where the center word is not a named entity. That is a location. So not all museums in Paris. This center word right here is basically not a named entity, and so we want that score to be low. And again, we could go through our training corpus. We find all the windows in our training corpus where the center word is labeled with a specific label, and then we can generate a lot of different windows where that isn't the case. So the idea here for our training objective is to really increase the score of the true window and lower the score of the corrupt window. And that will lead us to the following objective function. So we take the maximum of 0 or 1 minus the score of the correct window plus the score of the corrupted window. And if we minimize this overall objective function, what will happen? Well, either we can already distinguish very well whether a window is, has at its center location a named entity. If this correct score here, let's say, is 10, and the one of the corrupt window is just 5, then 1 minus 10 plus 5 is much smaller than 0. And so we'll end up in this part of the objective function. And if that isn't the case, if it still can't quite distinguish a true window from an incorrect window, then we basically go into this part of the equation and we'll try to minimize it. And minimizing this will basically maximize here the score of the correct window and actually minimize the one of the corrupted window. All right, so this is a continuous objective function, so we can use our standard stochastic gradient descent here and look at one window at a time. And of course, when we write this here, this is just one window, and our overall objective function is going to be a sum over all the different windows in the corpus. And the nice thing here of this one here is basically that once you're really good at distinguishing all the true windows from all the corrupted windows, that will be true up to a margin of 1. Sometimes you can set this actually as a hyperparameter too, and you say this is m, and you can set m to be half only. But in general, this will push all the correct windows to be up to a margin of 1 higher in their score than all the incorrect windows. And that will make it more robust. If you have something where the algorithm isn't quite certain, it'll be closer to the right side. All right, so what do we do when we have our feed-forward computation and we have our objective function? Well, we're just going to now take the gradients of our objective function with respect to all the different parameters in our model. So in this model here, we've had basically these two different scores, and both use a u, our vector here, the W matrix, and b, and our word vectors x. And so those are all the, we want to take the gradients of function j with respect to all of these. So let's go again, just as before. We start at the top and go all the way to the bottom of deriving those gradients. And so this is going to be the last really math-heavy kind of part of the class. So like after this, we really just use these as Lego pieces and we don't look again into them. So if something isn't clear, there's one really good advice that I've gotten before, which is if you're struggling with understanding in math, it's good to print this out and then close off each line and try to see if you could write down the next line by yourself, and then you compare with what happens next and so on. And I'll encourage you to do that if some of this isn't clear. So basically here we have the first derivative of s with respect to u is just in our product, so we just get our activation vector here for that derivative. And now it gets interesting. So let's look at the derivative for wij, which is the element of the matrix W at the ith row and the jth column. So we can rewrite here derivative of s with respect to the entire matrix W here, the gradient, and we can rewrite s as u transpose a, we can rewrite a as f of z, and we can rewrite z as just wx plus b. So this is just playing around with the notation here. And now the first thing we notice is that wij only appears in the computation of ai, the ith element of the activation vector A. So we'll use, for this illustration here, the following simple neural network, which only has 3 inputs, x, and 2-dimensional hidden layer A, and 1 output u. And so we're looking at W23, for instance, that really only appears in the computation of A2. Right? So you can look basically in this graph, but you can also think, okay, A2 is basically the second row of this matrix multiplication, which of course only the second row of W appears in that computation for A2. In general, Wi dot is the ith row of W, and hence appears in the ith activation of the next hidden layer. And here we use this notation of assuming that every input has, a +1 for a bias unit. So this connection right here we would call B2. Could anybody formulate a question yet, or yes?
Can you talk for a second about the difference between using U transpose as your scoring function versus using a different scoring function?
Yeah, that's a good question. So basically here you can use U, and now really it's up to you whether you use U here or a logistic. So for instance, a logistic unit would also just be logistic of some vector transpose times your activation, right? So this would still be a U, and that would work well if you have 2 classes only, right? Your probability is higher, probability is low, right? The sigmoid being just mapping between 0 and 1, and right at 0.5. And so now if you have more than 2 classes, you're going to want to have multiple scoring vectors. So you could actually have different U's, or you could then just go to the softmax and try to normalize all of them. And so really the softmax is nice in that it gives you probabilities and certainties about which class is which. But in many cases, all you care about is the maximum value. And so the softmax, the more classes you have, the more computational time you have to spend on computing that normalization factor, when really you only care about the maximum value of this. And so U is nice in that it doesn't require an exponent, which is a costly kind of function, and it just gives you, if it's very high, then that's the right class. And you can have different U's as well and different scoring functions as well. So you could, for instance, the corrupted one here could be a sum, or you could have a sum over these where you take the score of all the other classes that are wrong and you want to lower all of those scores and just maximize the one score of the correct class. Another sort of interesting problem that we'll encounter in the next lecture is the so-called vanishing gradient problem. We'll go over that soon, but basically whenever you take an exponent or you have a nonlinearity, it actually in many cases for most nonlinearities, less of the gradient arrives at deeper layers. And that isn't the case if you just have a nice linear function without a nonlinearity at the top. Yeah.
What if there were multiple correct classes? Would you still want to use softmax?
That's a great question. So if you have multiple correct classes, there are a couple of things you can do. One, the most common one that you would use is just training multiple binary classifiers and just say, for this input, is this true? Yes. And another input could also be true. So you could just have, a binary classifier for each class, and you just want to maximize that binary classifier for all your different classes, and you have here, for class 1, and then you have another one for class 2. And you can actually, and this is something that we'll also cover in the next lecture, you reuse the same hidden layer and just change the last layer and have multi-class, if you have multiple correct classes that way? Yeah, it's a great question. All right, so this is going to be our sort of toy model now to go over these equations and try to derive the first couple of steps of the backpropagation algorithm. So, like we noticed, like I said, we noticed that in the U transpose A, if we take the derivative with respect to Wij, really only the ith component of the vector A matters, and hence also only the ith component of the U vector here. So this inner product, we can basically only look at this element of that sum. And now we'll just basically, use standard, calculus and the chain rule. So if you have here, this right now is just a constant with respect to, our Wij, so we can pull that one out. And now AI was basically defined in terms of f of z, and z had its own definition, so we can use the chain rule and basically write out the derivative of AI with respect to Wij as the derivative of AI with respect to z, and times the derivative of z with respect to Wij. Now A was just f of z, and so what we'll write here is basically just f prime of zi, right? F is some function. It takes in as input a single real number. So f prime we'll just use as shorthand notation for the derivative of f. And one thing that we'll actually try to cleverly do is use functions f as our nonlinearities, like the sigmoid or logistic function, and those are synonyms, that actually have a derivative that can be computed using the actual function value. So f prime of z in our case of the sigmoid function is just f of z times 1 minus f of z, which is very convenient because then we don't need to compute exponents again. It's a very simple operation. But so this is just f derivative of f of z with respect to z. It's just f prime. And now we can write out zi here, and zi was basically just the ith row times x plus the ith element of bi. And so far, we have only basically used the chain rule once and replaced this in notation. So nothing too crazy has happened yet, though the slides start looking like a lot has happened. All right, so now this is where we were. And now the derivative of zi here that we just wrote out explicitly is very straightforward. That's basically bi is again a constant right now, and so we just can get rid of that. And now this is just a sum over all the k elements of the ith row, so over all the column elements here of the ith row times xk. And that, of course, is just xj for the jth element where this appears. So now we are going to define, and this is the first important step of backprop, we're going to define ui times f prime of zi as a new local error signal. Sometimes you can also call it an error message. And that will be our delta I. And we have xj, which is our local input signal. All right, so now we have the derivative of the score with respect to one element of our hidden matrix or hidden layers matrix Wij. And that's basically delta I times xj. So now, of course, we wanted to have the combination of all the rows and all the columns of this matrix. So what could we do to get from one element of that matrix derivative to all of them? Yeah?
Take the outer product.
Exactly. We take the outer product. So here, if we take the outer product of delta, which is a column vector, times x transpose, which with the transpose is a row vector, we have now a 2 by 1 by 1 by 3 matrix multiplication, and that will lead exactly to a 2 by 3 dimensional combination of all these different derivatives. And this is sort of, the interesting step that you often have to learn and see. Really, we go through all the potential examples that exist, but you take the derivative with respect to one element of your vector or your matrix, and then you see how you can generalize that. That is sort of one simple way of going about that. And now we again define delta here as our error message or error, local error signal or responsibility for each activation A. So basically, the delta can be interpreted as, how important was that AI for the final error? And that is going to be true for all the deltas that we'll define throughout the entire lecture and subsequent lectures. Okay, so now for the final element of our hidden layer, we have also our biases. And now we'll see that basically all the steps repeat. So we have here the ith element of the bias. Also, it only appears in the ith element of our activation layer. So we can redo the exact same steps. And basically, at this step right here, derivative of bi with respect to bi is just 1. So we just end up with delta I. All right, well, that was almost all of backpropagation. It's really just so far, taking derivatives and using the chain rule. It's really amazing how much we'll be able to do with this in the next 2/3 of the class. The main remaining trick is that we can reuse the derivatives that we computed for higher layers in computing derivatives for lower layers. So the last remaining layer for this simple model here is the word vector x. But after that, we'll go to having another layer below that. So it's important to really appreciate the slides and the equations that are going to come up on the slide here to then get to the next layer. And then we'll basically be done. Yeah.
So, I have a general question. So what do we actually minimize? Because for other machine learning models, there's a statistical or mathematical meaning of what we minimize, like SVM, you minimize the margin. For neural networks, what is the mathematical thing that we minimize?
Mm-hmm. So we minimize this mathematical objective function here. This is our error loss, and we're trying to essentially actually maximize the margin between the correct window and the incorrect window. So this is basically it. This is a very simple mathematical function that is defined fully with these 3 equations, and that's the objective that we want to minimize. And instead of having here a single u here, you could also replace this with the softmax error. In fact, I think that's what you have to do in problem set 1, and then you would minimize the cross entropy error at this. So the negative log likelihood of this. And in some ways, both will give you a classifier. Does that make sense? Yeah.
I think maybe you already answered this question, but to get the corrupted window, you're only considering nouns, right? So that you could.
Oh no, it could be any window in you have a set of windows where the center word is is a correct one, right. And basically any other one in the corpus that you have, you could consider a corrupted window.
So can you kind of prune the ones you might consider by doing some tagging so that you're not doing all these? I don't know. So if you're not going to consider that in as a named entity or a location.
Mm-hmm. Yeah. So you kind of assume that those are your incorrectly labeled examples, okay. And you kind of want to classify those as being in the other class, which isn't the named entity.
Okay. So you do it for all. Okay.
Yeah. And that might also answer your question, which is, you basically want to maximize the margin and push all the windows that aren't, that don't have as their center a named entity in one part of your vector space, and all the other ones, and then you have a margin between those, and all the ones that are correct are in another part of your vector space. Yeah.
Does that objective apply to every pair of good and bad windows?
Mm-hmm.
Could that be like a prohibitive number of windows?
That's a great question too. So just as what we did with the word vectors here, in the word vector case, we had one correct pair of two words that actually appear in a context, and then a bunch of pairs that don't appear in the right context. It's actually very similar here, with the difference that in the case of named entity recognition, you only have a small set of correct windows, whereas in the word vector case, you have an infinite number of correct windows as well as incorrect windows. And so what you would often do here is actually have a sum over, maybe we can write that out. So if you have multiple ones, we have here max of 0, 1 minus score of a good window plus score of a bad window, and now we can actually sum over multiple bad windows for each good window. Because in some sense, we can generate lots of bad windows very easily.
But not every bad window, just this.
Yeah, oftentimes you'd have maybe 50 or so, because if you have too much, you kind of start overfitting on just that one example. All right, so we now know the mathematical function we're trying to minimize. We have taken the derivatives with respect to all the other parameters of the model, u and w. And now we are going to take the derivatives with respect to the word vectors x. And to keep this example simple, we'll just take, again, the derivative with respect to one element of x. We already learned in previous class, in the previous class, what happens when you have multiple vectors and how to, basically split them and then update the different word vectors that are coming from a window. The first thing that we'll have to note here is, of course, that each xj appears in both of those hidden units, right? So x2 appears in A1 and in A2, and so do all the other ones. And so we cannot just use a single element here. We have to basically sum over both of those hidden units. And now let's go through this here again, and this is, I think, one of the last ones where we really write down all the details. So you do want to make sure you follow this equation. So basically here we have the sum over the two hidden units, derivative of s with respect to a 1 times derivative of a1 with respect to xj plus a2. And now we again will just write out our definitions from our neural network function. So s was just an inner product with respect, inner product times a. And basically with respect to a1 ai here, that is just ui. And now the a was just f of what's inside z here. And so we basically, this z here, we can again define as just one element and just write f prime. Again, that will just be derivative of that single number. It's just a function and has a certain derivative at a certain value. And so that's basically ui f prime. And then we take the derivative of xj of what's inside here. And that is, again, we can drop the b here. And that is just, again, an inner product with, because we're looking at only the ith element here, it's just inner product with the ith row of w. And when you write out that inner product, that will just come out to be wij. All right, so now what we'll notice is that this delta here is, this delta is exactly the same delta that we had before. Right, so this delta here is ui f prime of zi, and it turns out that's exactly the same one that we needed for the layer below, right? So this is one of the main insights for backpropagation. Turns out if you take of any recursive function something deep inside that function, you want to take the derivative of that, you have to go through the same steps as you did before, plus one extra layer. And so now we can look again at how we have this multiplication here, and whenever we have such a multiplication, we can rewrite this as an actual matrix vector product. So what would the matrix vector product here B. There are actually two choices, and one is going to be more convenient for notation than the other. Exactly. W almost transpose delta. So right now we just took the derivative as you're one step ahead, which is we took the derivative with respect to one element of J. So that will just be W dot J, so the jth column of W transpose times delta. So this again just comes out to be the same. And again, we reuse here the same vector of error messages delta. All right, so now, yeah, you gave away the next question, which is what is the full gradient of all the x's, and that will just be the full product of W transpose times delta. And this W transpose times delta is something that we'll see now in 3 slides or so for arbitrarily sized or arbitrarily deep neural networks too. So one observation that we want to make here is that the error message delta that arrives at a hidden layer basically always has the same dimensionality as that hidden layer. So the delta in this case came in from basically right here. This is where that delta arrives, and so it has 2 dimensions because this hidden layer is 2-dimensional as well. All right, are there any questions so far? All right, so now let's put this all together, and then we can move on to a deeper neural network. So we basically had here our full objective function for a single window, and we basically can now write down all the gradients with respect to this objective function. And one important step here is that we first check in the forward propagation, as in we'll take our window, this window, we take the corrupted window, we forward propagate them, we basically compute the scores here. And if the scores, if 1 minus score of the good window plus the score of the corrupted window is already lower than 0, then we just end up at 0. And then we don't even have to run backpropagation, right? Backpropagation, derivatives of all of these things of 0 with respect to all these parameters is just 0. So we're basically done. And this is another huge advantage of using this versus the softmax. The max margin will allow us to run forward propagation after training, after a while. The elements that really need to be updated in backpropagation become smaller and smaller. Right? So the obvious example is where you just basically the model just learns, oh, Paris. Whenever I see Paris in the middle, this is a named entity, this is a right window. After training for a while, it's so good at giving Paris the right amounts of weights once you forward propagate through the network, that it basically gives it such a high score that no matter how you corrupt it, the corrupted windows will get a smaller score. And the nice thing there is that you can basically become more and more efficient over time in your training, and the training objective during its optimization can then focus on only the harder and harder cases and try to push the margin, push them into the right direction. So this is basically what we define here. The forward propagation checks if the margin is actually not satisfied yet. If this 1 minus score good plus score bad or score corrupted is larger than 0. If that's the case, then we basically start taking derivatives. And the same, what we have here for derivative, oh, this should be j, not s, sorry. The derivative of j with respect to u would be this whole thing. And so we basically just, subtract the 1 from this score and add the 1 from that score. Yeah, so this here should be j, sorry. All right, this is basically our first neural network, single hidden layer, backpropagation in all its details. Are there any questions? Yes?
So it seems pretty clear how this applies to a case where you have like one class or it's not in that class, like city names and then not in that class. But if you had some inventory of classes, how would you propose to combine them into a single?
It's a great question. So one thing you would do could be that you have u of the correct class for something, or maybe I shouldn't use correct. Let's call good times a plus u of one that isn't correct, so let's call it the bad one, A. And then you will actually sum over all the bad classes. So this is, where B is in a set of all the classes C except the good class for this example window. So this would be one generalization of that.
So now you're summing over, basically the bad examples are actually the bad U's, not sample.
Right. So now, it breaks it a little bit down with the definition of A. Yeah, we can go over that, I guess the multi-class extension maybe in another class. But this is basically the idea. You basically take all the other classes that you have, and you basically, each class has its own U, because you now have multiple. You can't just get away with one U. One U only gets you two classes. Once you have multiple, you basically do this. And you can kind of see what's going on here and actually think of the connection to the softmax, right? The softmax would have one U, and you had multiple rows in that U, right? And one row was the correct one, and you wanted to increase that score, or the probability of that one, to eventually, plus the exponent and stuff, go to 1. Whereas the other ones you want to push down and go to 0. Here the main difference is there's no lower bar. You don't have any exponents, so the bad scores can go arbitrarily low. The good ones can get higher and higher. And why don't they go to infinity? Because in most cases we actually have regularization that will push them back to 0. So it doesn't push them all, up to infinity. Are there any other questions? Because the next, it's only going to get deeper after this. All right, so two-layer neural networks, and basically the final full backpropagation. So let's look at a simple two-layer neural network. We have the same definition of a window for X, and we have the same scoring layer at the top. And we now have two hidden layers. So let's introduce the notation very carefully, because otherwise you'll go, it's impossible to take correct derivatives without the correct notation beginning. So we'll define our first linear layer, and we basically introduce these superscripts for different layers. And we often use this kind of notation where we have the parameters of a layer sort of next to the arrows, and here we have the different names of the hidden layers. And we basically have this simple matrix product here again, and now we apply our element-wise nonlinearity f to the output of that linear layer. And now Z2 is going to be W2 times A1, the previous layer, generally sort of layer minus 1 plus B2. So each hidden layer has its own bias terms. And again, we apply an element-wise nonlinearity. And we could essentially go deeper and deeper. And in some cases, really going like to 7 layers, or in some computer vision cases even to 20 layers, still helps. And it helps more than having wider layers in some cases too. And those are choices that we'll go through later in the class. And then now we can basically take again the simple inner product, but instead of with respect to just A1 or A, with respect to A2. So now this could learn more and more complex interactions. Intuitively, if we were in a high-dimensional space, what's going on here is that we can compute more and more complex decision boundaries, right? So in the beginning, a single layer neural network could just go, have this. This is just a softmax, right? Now a hidden layer might be able, one hidden layer might be able to, have something like this. And so this is, one hidden layer. This is just softmax. And now a very complex two-layer neural network might actually really say like, all right, this is one area here, and this is, one sort of very complex shape. So you're basically more and more likely to overfit because you have more parameters, and now it might have a harder time generalizing. So this is basically the definition of the two-layer hidden network. Are there any questions about just the definition? All right, just inner products again and element-wise nonlinearities, right? Same thing. So now we can, basically again take the derivatives with respect to this, and really not that much is different. So we can again write out the final function here in terms of either just each layer and write that out separately, or write it out as one complex function. So now here you have U transpose of f of W2 times f of W1 of x plus B1, and then you add here the bias term of the second layer. Or you can write it as this, or you can simplify f of this whole thing as just A1. Right? So again, we're just playing with notation to get warmed up and ready. And now, again, the first hidden layer, which used to be just Wij, is now W superscript 2 Ij. And everything here is the same also, right? You just, instead of having delta I xj, you have delta I aj. And now aj just happens to be also coming as a function from another application of nonlinearities and matrix products. But so far, the very top of the derivations here for taking the derivatives is the same. All right, and so basically in matrix notation, this now for the layer in W2 is also just the outer product, just as before. And this is going to be an important function because every single matrix derivative will actually, the gradient here of these matrices will have this form. It will be some delta message times the activation that start, that this W is usually multiplied with. So one thing that we skipped over here, but that's important notationally, is that in order to create this delta to a vector, we actually had to multiply each element of ui with each element of zi. And sometimes people also use f prime of subscript I of the z vector. They're equivalent. And so in order to write that out nicely in matrix notation, we'll actually use this little circle as the element-wise product, or also called the Hadamard product, between these two vectors. So this is basically just each element of this vector gets multiplied by each element of this entire vector. All right, so now the last missing piece to really understand all of backpropagation is to take the derivative with respect of s with respect to W1. And really, this is very similar to what we've done before, and it's getting more and more tedious to write out. So basically, the main difference is that we have, just as before, this kind of equation which we use to take the derivatives of the word vector in a single hidden layer, but now we also have f prime. Because unlike of x, where sort of our derivatives ended at x, W1 will also be inside another function. And again, we'll just apply the chain rule. It'll just get more and more tedious to write it out. And maybe in the lecture notes, we'll actually write out all the gory details. But after taking, again, very straightforward steps, we pull out things that aren't parameters, we apply the chain rule, and so on, you'll end up with a monster that looks a little bit like this, where you have the number of layers here in L, and you basically go down one layer, and you'll use that same delta that we've had before, but now because you apply the chain rule again, you have another f prime. So delta will be the same as we had before, but now we'll define a new delta for the next layer down. And then we'll again multiply that in an outer product with aj. So basically, once we put all of these together, and we again go very carefully through all the steps, and I encourage you to do that. And if we write it into lecture notes, like close it off and see if you can, fill in each line yourself, you'll get a new delta error message. And that delta error message will basically be W1 transpose times delta 2, which we defined in the previous slide, with an element-wise product f prime here of each of the elements of Z1. And so the last missing piece will just be delta 1 times x transpose, because x was the input to the first hidden layer in the definition right here. So in general, for any matrix WL at layer L, and at any internal layer L, and any error such as regularized cross-entropy error or our max margin error or so on, all backprops messages in a standard multi-layer neural network boils down to these two equations. So if after going through all your math you don't end up with exactly those two equations, something went wrong. So you have, every time you have your delta messages, and your delta message at the current layer comes by multiplying your W transpose times the delta message of the previous layer times an element-wise derivative of your activations at this layer. And then you'll always end up with this outer product of the delta message that came into that layer times the activation transposed. And if you have regularization, plus your lambda of your elements W. And you know, as we've seen, the top and the bottom layers might have simpler delta messages because there's no derivatives. X are just, you know, applied as is, and the top is just a linear layer, and that's simpler too. Or the softmax, in which case you just have yi minus your target times your activations. And so just to, you know, if that was a lot of math, and you know, I just want to summarize it maybe in one high level again, which is, again, it will just basically taking gradients with respect to our clearly defined loss function. In general, you know, it'll just be applying the chain rule wisely. And also, if computing your loss of your examples, given your examples and your parameters is O of n, then so is computing your gradient. So, you know, this is going to be, in general, a much cheaper sort of training algorithm than what you would have in probabilistic graphical models, where training is often quite complex. This is completely deterministic. Once you write down exactly your forward propagation, you can deterministically compute your gradients. Just using the chain rule, whenever you have two elements that one depends on, you'll have to sum them up. And again, you will compute first the derivatives at the top and then at the bottom. If you have multiple such elements in your hidden layer, then you basically sum over all of them to get the gradient of x. And you know, no matter what it is, if you have any directed acyclic graph, and we'll go to, that's basically all that the remaining lectures are. We construct more and more complex directed acyclic graphs of matrix multiplications. And so in general, we'll have any kind of computation. It moves forward. We have some input x, some label y. We go forward through multiple layers of nonlinearities. We compute some loss function, such as negative log likelihood or the margin loss. And then we will go backwards one step at a time. And we'll reuse the same computation for taking the derivatives. And you know, we went through all the gory details in the previous slides, and this is sort of a high-level overview of the same thing. And really, it could be, you know, any kind of combination. It could be, you know, this x could come in multiple ways, and it will just still be going backwards in the same way. And we'll end on the note that basically the nice thing is, because this is so deterministic, a lot of people have actually built automatic differentiation tools where you just define your neural network, and then you don't have to go through all the pain of doing this by hand, and you can just, you know, have this automatically be done by a computer. However, I think it's good if you once you understand this one main equation here, these two equations, there's no more magic in deep learning for you. You will get really what's everything that's going on, and it's basically, it boils down to those two equations in almost everything you do. So with that, I want to end and give you summary for the next lecture. Oh. So congrats, you survived the hardest part of this class. So this is, you know, everything else from now on is just more of those matrix multiplications and backprop. And in the next lecture, we can really go to town and start working on some really interesting models.